Okay. Okay, so away we go then. Back to our organization chart. So yesterday, I think it was, we talked about radiometric variables and all the radiance and irradiance and all of that stuff. And so today we're in the bottom box down here on apparent optical properties. So as we're going to see, and you already know, that's all these reflectances and K functions, and there's some other ones. So the bottom line to remember, which I think 90% of the people in this field forget, is that to be an AOP, you have to satisfy two conditions. First of all, AOPs are quantities that depend on the IOPs and the radiance distribution. So whatever light's in the water, is going to affect the AOP, and whatever the IOPs are is going to affect it. But the second half of the definition is that to be an AOP, whatever it is, has to display enough stability or regularity to be useful for approximately describing the optical properties of a water body. Well, what's that mean? So, okay, let's take the downwelling plane irradiance, ED. It depends on the IOPs. It depends on the radiance distribution. So it satisfies the first half of the definition. But you're measuring the ED here, the sun's out, you get some number, the sun goes behind a cloud, ED could change by a factor of 10 in 2 seconds. So there's no stability there. So, or regularity. So if you just show me a spectrum of ED that you measured in the water and ask Kirk, what's the chlorophyll concentration? I don't know. I can tell you, well, the water was kind of blue or it was kind of green, but that's about it, because that magnitude is so sensitive to things like sun angle or the sky conditions or whatever. So the ED is not useful as an AOP because it just doesn't have stability. So I've seen papers published where they say, we measured ED and this AOP gives us whatever. And I just say, ED is not an AOP. If you don't remember anything else from this lecture, just remember radiometric variables like ED or radiance are not AOPs because they're so sensitive to environmental conditions. Okay, the other thing to remember is that IOPs you can measure in a bucket of water. You did that last week. AOPs have to be measured in situ because they depend on the radiance distribution in the ocean. So you can't go get a bucket of water and measure, run it through your ACS and you get absorption and scattering, and then also measure RRS for that water body on the bucket of water. You have to measure the RRS in the ocean. Okay, the idea with an AOP is that it's going to depend weakly on external environmental conditions like sun angle, sky conditions, surface waves, and it's going to depend strongly on the water IOPs, because what we want to do with an AOP is eventually get out some information on what's going on in the ocean, like chlorophyll or absorption or whatever it happens to be. And historically, before the days of ACSs and things like that, it was really hard to measure IOPs, but they're easy to interpret. You give me the absorption coefficient, I understand what that is. This is less true today because we now have instruments for making IOP measurements. But in the old days, the AOPs were easier to measure. So you could go out, you could take an ED sensor, you could point it upward and get, or a plane irradiance sensor, point it upward, get ED, turn it upside down, get EU, take the ratio, get the reflectance. Okay, that's fine. I've got this. The problem is it was easier to measure that reflectance, but it was then harder to make sense out of what it was really telling me. Okay, in a perfect world, we would have this instrument where you would just go out, click the button, and it would measure the whole radiance distribution as a function of depth and time and direction you're looking and the wavelength and all of that. And then you would know everything there is to know about the light field. You wouldn't have to have an ED sensor or a PAR sensor. You'd just compute those things from the radiance. Well, of course, we don't really have the instruments to do that conveniently. And for the material properties, all you would do is measure the absorption coefficient and the volume scattering function with this magic instrument. You click the button, you've got it, you're done. You don't need an ACS to measure the scattering coefficient, and you don't need a backscatter instrument to measure BB, because you would just compute those things from the volume scattering function. Well, of course, we don't really have those instruments. And if you had these measurements, you wouldn't need anything else, and in particular, you wouldn't need AOPs. But the reality is we can't measure radiance conveniently, so we end up measuring other things like irradiances and PAR and so forth. And we can't just easily measure all the IOPs at once, so we come up with other things that we can measure that we can try to get the information we want. Okay, so here's how it works. Here's some plots of ED and EU. So the solid lines are ED and the dotted lines are EU. And there's 4 different sky conditions: the sun at the zenith, 30, 60, in a clear sky, and then an overcast sky. So you look at, let's say, the ED plots here. There's a factor of 10 variability between the sun being straight overhead in the blue and a heavily overcast sky in the purple. Or same thing with EU, a factor of 10 variability. So that shows you how sensitive ED is to sky conditions. And that's, once again, why ED is not an AOP. Yeah, Ben.
Can you remind me what ED and EU are?
ED is the downwelling plane irradiance, and EU is the upwelling plane irradiance. Okay, so once again, those things are not, irradiances are not AOPs. But you look at this and say, well, wait a minute. Look at the slopes of those curves. The slopes are almost exactly the same. It's just that they're offset in magnitude. So maybe if I take the slope of the curve, or just the depth derivative of the irradiance, maybe those will all look about the same. And so I will, by looking at the slope, I'm doing away with the effects of sky conditions. So here's what we do. You can always cook up an AOP. You think about, maybe if I did this, I'd get something useful. And that's a legit way to do things. That's all people did, was they looked at a plot like that and said, well, let's try the slope of these things as being some measure of what's going on in the ocean. So we take the depth derivative, dEd dz, that's the slope, normalize it by ED, and we'll call that this KD. So, and it's negative because this guy is generally, ED is decreasing with depth, so they wanted a positive number, so they just define it that way. And of course, a D something over something, that's D of log something. So you'll often see that KD is called just the log derivative of ED with depth. Okay, and notice, of course, whatever units irradiance is canceled out, and the K function has units of 1 over distance. So let's try that. And then we could do the same thing for EU or LU or any of those things, and you can come up with a whole family of K functions for downwelling irradiance, upwelling radiance, PAR, so on. And if you notice here, if you just take this equation here, multiplied by dz and integrate that, this definition of KD is just equivalent to saying that ED is the surface value and exponentially decaying according to this little integral here. And then if KD were constant with depth, which it never really is, but then this would just be surface value e to the minus KD times Z. And so a nice little exponential decay there. So either this or this are equivalent definitions. Okay, so let's look at some of these things. For those plots or simulations we just saw, here's K at 550 nanometers for various K functions. So the blue is KD, the green is K for upwelling radiance, K0 for scalar, the net ED minus EU, and K for LU. And then the sun is at 0 is a solid line, and the sun at 60 degrees is a dotted line. So you'll see that near the surface, the K functions are often substantially different. There's like a factor of 2 or so there. And you can see that for the sun overhead or at 60 degrees, yeah, there's differences in the K functions. And remember, yeah, Ben.
What is net? Is that?
Net is ED minus EU.
And LU is the income, right?
Well, LU is the upwelling radiance, and the K net is the irradiance difference, ED minus EU. And you're going to see that again with Gerson's law tomorrow or whenever it is. But anyway, these are four various measures of the light field, ED and EU and scalar and so forth, and their corresponding K functions. So they're different up here at the surface, but it looks like they're all coming together with depth. And this is for a particular chlorophyll of 1 in the simulations. Here's the same sky conditions with a chlorophyll of 5, and the same depth going down to 50 meters here. Now all the K functions are different up near the surface, but they're all coming together as we go down to depth, and it looks like these are doing the same. So actually what's going on here is that near the surface, the AOPs, in this case the K functions, are affected by the surface boundary conditions, meaning like the sky, solar angle, sky conditions, waves on the surface and so forth. But as you go deeper and deeper in the water, then scattering blurs out whatever those sky conditions were, and the AOPs all become IOPs if you go deep enough in homogeneous water. So here you're seeing big differences in the K functions at the surface, but they all went to, in this case, 0.19 per meter down here. And in this case, different chlorophyll, they went to 0.11 per meter as you go to depth here. So that's just a feature of how all AOPs work. Is it deep enough, you forget the surface boundary conditions, and they actually do become IOPs. But of course, unfortunately, we're usually interested in what's going on here near the surface, and then that complicates your life. So as I said, down here, in general, AOPs are determined both by the radiance distribution and the IOPs. Up here, you're seeing the effects of both. Down here, whatever the radiance distribution was for these different curves now all becomes the same. And so down here, they're determined only by IOPs. Okay, so people over the years have done a lot of work to try to model KD. So here's our definition, and if K were constant, or if you used an average value down to some depth, you just have a nice little exponential. So one of the first models for KD by Austin and Petzel back in the 80s is they came up with a little formula, and this is just a bunch of fitting to data, best fits to data, that KD at any wavelength, you could determine if you measured KD at 490, and then they have these tabulated factors, the M here and a KD for water term, and you can go look those up and plug them in here. And if you measure KD at 490, but you'd like to know KD at 440 or 650 or whatever, you can get it from this little formula. And KD 490 is a standard NASA remote sensing product. So when you go look at your MODIS data or your VIRS data, and you get out all of this stuff, chlorophylls and so forth, and one of the things you get out is what was KD at 490. So first question, why did they pick 490? Why not 550 or 440 or something? It's a trick question because you guys weren't born yet when they decided this, but it's because back in the old days, 60s and 70s, there was great interest in being able to spot Russian submarines sneaking around in the North Atlantic. And one way you do that is with LIDARs, and there's a LIDAR at 488 nanometers that they would fly over and hope that they could bounce the LIDAR off of the submarine. And there was filters that measured sort of centered at 490. So 490 was close enough to 488 that if you knew this, you could evaluate how deep your LIDAR would penetrate into this nice open ocean water. And so that's why it got to be 490. Well, and then who cares about KD anyway? Why bother to measure it? Well, that's because that if you know KD, you can predict the irradiance with depth. And as we'll see tomorrow, that knowing the irradiance at depth is what runs all your ecosystem models where you grow phytoplankton and so forth. So here's another model for KD, this one from Andre Morel, where he predicts the average KD over the depth of the euphotic zone. So that's his KD bar. And he comes up with a little formula where you plug in the chlorophyll and there's a little coefficient, there's a little exponent, which he tabulates here. Once again, fitting to a bunch of data. And he comes up with little functions so that, for example, if you want the average KD over the euphotic zone at say 440 here, he gets a pretty good curve. Here it is at 510. And so people take these kind of formulas, plug them into their ecosystem models to get the light field at depth, and then use that to do their photosynthesis and so forth. So that's why people care about KD. Okay, here's just another model of Zhongping Li, where he did like 1 million hydrolyte simulations, and he comes up with a fancier function that has, I think it's 5 parameters here, these M naughts and gammas and M2s and so forth. And he did all these hydrolyte simulations, did a nonlinear least squares fit to determine these coefficients. And then he comes up with a formula where you can plug in the backscatter coefficient and the absorption coefficient and get a value of KD. So there's a bunch of these models out here, and here's the profiles of KD versus predicted values, and they're pretty good. And then here's the actual hydrolyte values versus the prediction. And so this is the kind of curve that he used to determine his fitting coefficients. Yeah. Is what?
What is gamma emitters?
What is gamma?
Oh, gamma is just an unknown coefficient. So the M1, M0, M1, 2, and 3, and gamma are his 5 different coefficients. And why he didn't call that M4 or something, I don't know. But anyway, it turned out the best fit value here was 0.265. So it was just a free parameter that he used to fit the data. Yeah.
Can you choose which one of these models you want in hydrolyte?
Well, hydrolyte doesn't have any of these models inside it. It was being used for putting in different chlorophylls and such, computing the K functions and then fitting those K functions to this model to determine the coefficients.
Okay.
Yeah. Yeah. Then.
EPW.
Oh, that's the backscatter coefficient by water.
Backscatter coefficient.
Yeah, at whatever the wavelength is. Okay, enough said there. So think about this. You want to go out and measure ED in the water, but when you make real measurements just below the surface, you have wave focusing as a simulation of how the ripples on the surface either focus the sunlight and make a really bright spot, or they actually make a dark spot. So you've got your instrument down here, and it might be very dark 1 second, sort of average a minute later or a second later, then really bright for a second. So if you want to take something like an ED measurement, right near the surface, you have a lot of noise from wave focusing in particular, or there may be bubbles in the water or whatever. So you may start making your measurements, say at 5 meters, and go downward, and you make your ED measurements, and then from that ED profile, you get a KD, and then you want to use that KD to extrapolate back up to the surface. So is that likely to be very accurate? You know, even if you assume the water is homogeneous, you're using data down here and you're computing a derivative of the data, namely DED, DZ, and derivatives are just kind of inherently noisy things. So you get a KD down here, and then you'd kind of like to work your way back up and figure out, well, what was really ED here at the surface on average. It's a really hard thing to do. And once again, people have spent enormous amounts of effort trying to figure out how to take measurements at depth and then extrapolate back to the surface. And the answer is just, there ain't no good way to do it. Extrapolation is always an iffy proposition. If you've got a bunch of data and you want to, you know, starts here and it starts here and you've got points in between, you can interpolate very well. But when you start trying to extrapolate past the end of your data, it often just goes really bad in a hurry. So keep in mind, if you're doing something like trying to get a KLU, which you can use to extrapolate LU up to the surface and get it through the surface to get a water leaving radiance, so you can then compute RRS. And you started your LU measurements down at, you know, however many meters down, and then you try to extrapolate up to the surface with a KLU. Maybe you'll get it right, but you may easily be off by a factor of 2 or whatever. It's just a hard thing to do. Okay, another thing here, we've now talked about beam attenuation, but now we've got diffuse attenuation, and they're not the same. So beam attenuation C is not the same thing as diffuse attenuation K. So think of it a couple of different ways. Here we're at one depth and here's a deeper depth. And if the light field's going downward, you know, we have some ED. So the light fields, the radiance is going more or less downward. So like the sun's straight overhead. Then we go from here to here. You get an ED at this depth and some ED at this depth. But if the sun's off to the side so that the radiance is coming in at an angle, you get an ED here and an ED down here. But this path length is shorter than this path length. So even if these EDs were the same here, this ED here is going to be greater than this one because this one has gone through a greater path length and it's had more chance for the light to be absorbed. So the fact that this ED is greater than this one is going to mean that this KD is less than the KD for this one, even though the beam attenuation is the same in both cases. Another way to think of it is, let's say you're going to measure beam C. Well, you do that with a narrow, small field of view instrument, like on the C side of your ACS. So you've got this light that's coming down and you have your instrument with a narrow field of view. So it only sees the beam of light that goes from here to here into the instrument. And this beam of light misses the instrument, and this one misses the instrument. And whatever light is scattered out of these beams is not seen by the instrument. And even the light that's scattered from here would go into the instrument, but it would be blocked inside because it's outside the field of view. So you come up and you say, how much light got from here down to here? And you use that to compute the beam C. Now over here with an ED collector, it can see the light coming from the whole hemisphere. So it sees the same direct beam coming straight down as this one. But now the neighboring beams out here that are scattering, they're also adding to this instrument. And even though this direct beam might scatter some light out, the neighboring beams can add it back in. So this guy is going to come up with a bigger measurement because it's collecting light from a whole hemisphere, not just from a narrow set of angles. So you will always find that beam C is greater than KD because KD is able to collect more light from all directions, and therefore it looks like the light going from here to here has decreased less in magnitude than just the radiance. So just keep in mind that beam C is always greater than KD. Okay. These K functions do have their virtues, you know. They're determined by rates of change with depth, so you don't need to absolutely calibrate your instrument. You're just looking at the slope of the curve, not its absolute magnitude. You can work through the theory, which we're not going to do in here, but it turns out KD is a very absorption-like parameter. So it's very dominated by absorption, and absorption is dominated by chlorophyll in case one waters. So KD correlates very strongly with the chlorophyll concentration. Howard Gordon had a paper where he showed that about 90% of the water leaving radiance comes from a depth of 1/KD, which he calls the penetration depth. Now, of course, that depth depends on wavelength because KD depends on wavelength. But if you get good, you can actually, a guy like Howard Gordon can walk out on the dock here and look at the bottom and say, oh, well, I see the bottom at 3 meters or 1 meter, and figure, well, that's at the clearest wavelength, it's green. He can come up and tell you what KD is and actually do a pretty good job of just eyeballing something like the chlorophyll concentration. And then there's relations between various Ks and reflectances and so forth. We'll see one of these tomorrow in Gerson's equation. What's not good about them is that they're never constant with depth, even in homogeneous water. So the IOPs can be independent of depth, but the AOPs or K functions will always depend on depth, at least near the surface. And their greatest variation is near the surface. And we're computing a derivative, and it's always hard to compute derivatives when you have noisy data. So then you end up saying, well, I'm going to have to do some kind of smoothing, but then that opens a whole nother can of worms. Okay, let's go back to this plot. A minute ago, we were looking and saying all of these have about the same slope, so let's try a depth derivative, and that's what we got KD from. If we look at the downwelling and the upwelling planar radiances, and you look at the ratios, so here for the blue curve for upwelling planar radiance and downwelling planar radiance, and you look at the ratio of, say, up to down, that's about the same as it is for the sun at 60 or the overcast sky. So the ratio of EU over ED seems to, at least looking at this, be almost the same. So that's another way of normalizing out the sky conditions. So we can say, let's try looking not at a depth derivative, but looking at the ratio of these two radiometric variables. And that's our irradiance reflectance. So here's EU over ED is irradiance reflectance. So that's a measure of all the light going downward, comes down into the water, it gets scattered, some of it comes back upward, and we look at all the light that is going back upward, and then whatever that ratio is. So we take a look at that. Well, here's R at 555 for the chlorophyll of 1, and these 4 different sky conditions. And you notice once again, the solid here was for chlorophyll of 1, and the dotted is for chlorophyll of 5. So they're different values, of course. Up near the surface, once again, they're influenced by the sky conditions, but the deeper you go, they all come together because in the case of the high chlorophyll, there's more scattering. The more scattering redirects the light, it forgets where the sun was, and they all come together and once again become IOPs. So that's a possibility for a decent AOP. Clearly the values depend on the IOPs. They do depend on the radiance distribution, but only really close to the surface. All right, so here's a bunch of irradiance reflectances measured by Professor Russler back in '95 in the classic paper. And so here's what ours looked like in estuarine water, fjord water, coastal water, open ocean water. And you can kind of look at these curves and say, well, open ocean water looks a lot different than the fjord, which looks a lot different than an estuary. So we're now learning something about what's going on in the water from just looking at the shape of the curves here. And now the next step will be to take some kind of ratio of wavelengths or some sort of inversion model or whatever. And we might be able to take one of these curves and back out something like chlorophyll or the absorption coefficient. And Colin will have a lecture on that, and you're going to do a lab on that next week. Ben?
Yeah, I was wondering, the estuary has some shapes that don't match kind of the red average in the same way that the coastal oceanic and fjords their average kind of all matches the shape.
Yeah, I think this was in the San Juans there.
Yeah, it's in the San Juans community. So it's not really an average. I selected for examples from those curves as representing extremes. And so it's a test of a model. Like if you can do it in a worst case scenario, it should work for the least extreme. So it's not meant to be an average. It's meant to be like, hey, that's really really different from ocean.
Thank you.
Okay, so now the next question, well, how does this irradiance reflectance depend on things like sun angle, wind speed, sky conditions, et cetera? So here's some hydrolite simulations where I did chlorophylls of 0.1, 1, and 10, sun at 0 and 50 degrees, and a clear sky and an overcast sky. So generated all of these spectra for R, and this is at depth 0, just below the surface. So what you see here is there's three groups of curves. Here's the one for the chlorophyll of 0.1, here's the ones at 1, and here's the ones down here at 10. So you see I can separate the three chlorophyll groups pretty well. And then there's a little bit of variability within each group that's due to sun angle and sky conditions. So I'm starting to see, oh yeah, I've got a pretty good AOP here because the variability due to the chlorophyll concentrations is a lot bigger than the variability this little bit, or this little bit due to the external environment. So that's what I'm looking for to make a good AOP. Okay, we can actually do one better. There's this water leaving radiance business that you now know about. And so here's the sun, it puts an ED onto the sea surface. Some of that's reflected upward, that's surface reflectance. Some of that light gets into the water, gets absorbed, some of it bounces around, finally gets back out, and that makes LW. And then the irradiance reflectance is LW divided by ED. So that's something we could try as an AOP. It's a ratio of radiometric variables. And notice if the sun goes behind a cloud and ED goes down by a factor of 10, then LU or LW is also going to go down by the same factor of 10. So we get rid of that sky condition by that normalization. So we try that, and people often just work with the nadir viewing RRS, but it actually depends on whatever angle you're looking at, this direction, that direction, whatever. They'll all be at least a little bit different. So if we do that plot again, now look at this. We have a really nice separation by chlorophyll values and very little variability according to sun angle and sky conditions. So this guy is a really good AOP. And this is the reason that everybody now uses RRS rather than irradiance reflectance to do their ocean color remote sensing. The catch is that you have to have two different instruments and they have to be well calibrated, because you have to have one instrument that measures the upwelling or water leaving radiance and a different instrument that measures the downwelling plane irradiance. So that's like on the TSRB, you've got an irradiance sensor up here above the surface, and then you've got an LU sensor below the surface. But those guys have to be well calibrated. Whereas with the irradiance reflectance, you take the same instrument, you point it upward, you get ED, you point it downward, you get EU, and even if this guy's off by a factor of 5, that factor cancels out when you do the division. So that's why people started with irradiance reflectance, is they had plane irradiance sensors and they didn't have to have great calibration. But then once they got sensors that they could calibrate well enough that you could trust the absolute values of ED and LU, then you switch over to this and you get a really great separation and very little environmental effect. Now, these curves are the effect of external environment. They're still, and that's just comparing the old and the new, there's still an effect of viewing direction. So here's now different viewing directions where you're looking at the nadir direction, 30 degrees off nadir in this direction or that direction or that direction. And now in some cases, like the low chlorophyll, those viewing directions don't make much difference. But at the high chlorophyll, now there's a pretty big difference here depending on the viewing direction for a given sky. And the reason is that in the high chlorophyll water, you've got a lot of scattering. Scattering is determined by the volume scattering function. So when you look in this direction versus this one, you're actually getting light that's sort of sampling different angular parts of the volume scattering function. And so there's going to be this thing called the Brdf correction that you'll see again in a later lecture, Friday, I guess, that it tries to correct for the fact that we also have a dependence on the viewing direction, not just on sun angle and such. Ben?
Going back a few minutes, what is the difference between radiance and irradiance?
Well, radiance is looking at a small solid angle, so it's watts per square meter per steradian per nanometer. Irradiance, you're getting the light over the whole hemisphere, so it's watts per square meter per nanometer. No solid angle in the denominator. So go back to the radiometry lecture Monday or whenever it was, where you define the radiance and then you take the, here's my my instrument. I've got my detector down here and the tube here that's blocking light from those directions and just letting that direction come through. Then I take this tube off and now my sensor's getting light from any direction, and that's the irradiance. Okay, so this is better than R. RRS is better than R, but it's still not perfect. It still does have a viewing angle effect. Okay, you've already done this. You've learned how to go out and say, oh, okay, the sun's over here and I want to do this business with, measuring the sky, measuring the surface and all of that. And it just kind of turns out that the best angle, if the sun's here, you don't want to look there because you get specular reflection off the surface. You get still a lot of specular reflection at 90 degrees. And something like 135, looking down in this direction, is where you get the least amount of specular reflection of the sunlight. Why not look at 180 degrees away? Then you would get almost no specular reflection. So why not put the sun there and point your instrument at 180? Yeah, because you'd be looking at your own shadow. So a lot of people just say, well, sun's here, it's easy to figure out where 90 degrees is. I'll make my measurements here. But you're a little better off to go around to 135 and then look at something like 30 or 40 degrees off nadir. That's when you get the minimum amount of specular reflection. And of course, the problem is the sun's here and there's a cloud there. That's not going to work so well. Maybe, you do go over here, or maybe if you look in this direction, there's no cloud. You just kind of have to figure that out at the moment. But anyway, you've seen this geometry yesterday, playing with it in the field. And there's this quantity called the Brdf, Bi-Directional Reflection Distribution Function, that we'll talk about in week 4, I think it is. But it's a measure of how a surface reflects light. It's basically the IOP for a surface as opposed to being an IOP for a volume of water. But basically you have light that comes in, it hits the surface, it reflects off, and you define this quantity. So that's telling you how reflection's going in from a given incident direction into a given reflected direction. And that's where this term Brdf effect comes in. So, yeah.
How is that different than the rho factor that we were?
The rho factor is a fudge factor that says, I'm looking down in this direction, I measured my sky and I measured my water, and I'm really on the water. I'm getting all this light from different directions. And I just kind of need to know how much of that was coming up into my sensor. So I did all these simulations and you come up with some number like 0.028 or 0.04 or whatever. And it's just, in all honesty, it's a fudge factor that tries to account for light coming from all directions reflected into the one I was looking at. And that's a measure of reflectance. This guy is for light coming from one direction reflected into one direction. So that rho factor is kind of an integral of the Brdf over all the incident directions and into one direction. And when you look in the literature, there's at least 15 different kinds of reflectances that different communities talk about. And I won't trouble you with the other 13, but these are 2 different measures of reflectance that aren't really quite the same thing, and they don't even have the same units. That rho's non-dimensional. This guy will actually turn out to be dimensional, and you'll see more of that next week. Okay, so what people try to do is when they look at this and say, well, there is an effect of viewing direction, and of course, I'm going to hold the sun here and I'm going to look here, 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 and then I move the sun and look here, here, and here. I get something a little bit different. So they try to come up with a way to some way normalize out this angular dependence here. And so what Morel did was he said, what we would like to do is take this remote sensing reflectance, which is going to be measured for some particular sun angle, some particular viewing direction, and we want to normalize it to a common value that would be, for water leaving radiance, the radiance that would be measured by a nadir viewing instrument if the sun were at the zenith and there were no atmospheric losses due to absorption. So in other words, Morel says, I made my measurement over here, the sun was here, I was looking there. Somebody else comes along, they make a measurement, the sun's over here and they're looking over there. It would be nice if we could take those 2 different viewing geometries and normalize them to where it was like we were all looking straight down and the sun was straight overhead and there was no atmospheric absorption. So that's what he's going for. So, and of course, you make a measurement of LW and you do it in July and then you do it in January. Well, even things like the Earth-Sun distance will make about an 8% difference over the course of the year. So he wants to get rid of all of these effects. So he did a zillion simulations and he says, okay, you give me the water leaving radiance that you measured for your sun angle theta S, your viewing direction theta V, and then the phi is the difference in the sun and the viewing direction. So that's what you measure in the field, a particular day. Then you normalize that. R is the Earth-Sun distance. So you take whatever your Earth-Sun distance was at that day of the measurement and normalize it to what it would have been at the average Earth-Sun distance over the course of a year. He divides through by the cosine of the sun angle theta, and that gets rid of the sun's zenith angle effect, because if the sun's up here, you get a bigger number than if it's over here. So you divide the value over here by the cosine, and that's essentially moving the sun back to the zenith. And then he's got a little atmospheric transmission function that says, well, in the real world, I lost 3% of my light due to absorption by atmospheric gases and aerosols. So I really had a transmission of 0.97 because I lost 3%. So let's divide by a transmission of 0.97, which will make it like the atmosphere is not absorbing. So he takes the measurement, plugs in these things, and you know where the sun was, you know the Earth-Sun distance, you model the atmosphere, and he comes up with what he calls the normalized water leaving radiance. Notice that it still depends, though, on the viewing direction. So that's kind of the first step. And then he does a bunch more calculations, and he says, well, you know, the wind was blowing at 10 meters per second when I made my measurement, and it was 3 meters per second when you made your measurement. It would be nice if we could normalize those two values to where the surface was level. And so he did a bunch of simulations and came up with this little fudge factor that says you plug in the wind speed W and your viewing direction, and this factor here will normalize it to nadir viewing and no wind direction. And then he has these factors F over Q, and they're sort of there for historical notation reasons, but that's what they get called. But what they do is they say, I've got certain IOPs here, whatever the chlorophyll was, and the wind speed, and I have an atmosphere here. So for a particular atmosphere, particular wind speed on the surface, a particular chlorophyll concentration, this factor here will normalize it to where, for my sun angle and my viewing direction, it would be like I was looking straight down with the sun straight overhead. And these are just big lookup tables computed once and for all using, guess what, hydrolite. And then when you do this correction thing, you go off to the lookup table and you say, well, the wind speed was 5, the sun was at 45 degrees, I was viewing it at 30 degrees off nadir and 135 here, and you look up the magic number that converts this into what he calls the exact normalized water leaving radiance. Well, it's not quite exact. It's exact for whatever the water in the IOPs were at the time of the measurement, and that depends on chlorophyll. So you kind of have to do a first guess at what the chlorophyll was, then you correct here, you get a water leaving radiance, you get a better reflectance, then you take that reflectance and you get a better chlorophyll guess, and then you redo this, and after 2 or 3 iterations, you finally decide you've got a good chlorophyll that's consistent with everything. And that's what Friday's lecture is going to be about, how NASA does this stuff. And you finally end up with what gets called, they take this normalized water leaving radiance here, and they multiply by pi, and they divide by the extraterrestrial solar irradiance, F0, and they get a non-dimensional reflectance, which gets called the exact normalized water leaving reflectance. And this is the quantity that NASA does all of their remote sensing retrievals on. and you'll see how that works on Friday. Now, if you're an amateur linguist, you'll say, wait a minute, I can have a water leaving radiance because radiance actually leaves the water. Reflectances don't leave the water. Reflectances are a property of a surface. Well, it still gets called water leaving reflectance. So it's just the surface reflectance computed from the water leaving radiance. And I'm pretty much the only guy in oceanography that worries about these word usages.
And Robert's one. Robert is very excited.
Who?
Robert's one.
Okay. So anyway, now what we've done, of course, everything here still depends on wavelength. These Morel Brdf correction factors, and this whole thing here is what gets called the Brdf correction. They require knowing the chlorophyll concentration, and they've only been computed for case 1 water. And they're only tabulated for the wavelengths that NASA needs for CWIFs, MODIS, and VIIRS. So you go into case 2 water, you got this nasty stuff in some bay somewhere, you apply these and you hope for the best, but they're really not tabulated for case 2 waters. And then you've got some other wavelength band for your Maris instrument or whatever it happens to be. Well, maybe you take the 2 adjacent wavelengths here and interpolate or something and hope for the best. But that's the state of the art for what NASA does. Emmanuel.
There's also Bi-Directional, the Irradiance that are capable of coastal.
Okay. So anyway, we're going to see a bunch more of this on Friday. How much difference does this whole business make? Well, the dotted lines here are reflectances for a particular sun angle, particular viewing direction, and 90 degrees azimuthal direction from the sun. And then the solid line is after doing all these Brdf corrections and everything. And you see in very low chlorophyll water, it doesn't make much difference. As the chlorophyll gets higher, the difference becomes greater. So the higher the chlorophyll, the more important it was that they did this normalization business. But that's typically kind of how much difference it makes. And you might say, well, you know, who cares? That's not much difference. But NASA's trying to get the very best values possible, because this difference between here and here might be the difference in retrieving a chlorophyll of 4.5 or a chlorophyll of 5.0, you know, yeah.
And so we might expect in case 2 waters that this actually would be really important.
Yeah, it's going to be more important in case 2 waters, but at least at the moment, NASA doesn't deal with that when they apply the Brdf correction. Yeah, Anna.
Rho here is just RS.
This is basically RRS with some, I think actually the next slide here, yeah. If you want to simulate this thing in hydrolite, you do a hydrolite run, you put the sun at the zenith, you compute hydrolite's RRS, and you multiply by pi, and that gives you this Rho thing. And that's actually how Morel generated his lookup tables. And Morel told me one time that he estimated he had done over 1 million hydrolite runs. And I thought, man, I blew it. I should have set hydrolite up to charge $1 per run instead of charging you once. Now, he didn't sit there and go through the user interface 1 million times, but, you know, set up a big batch job. But that's basically how he got the numbers he needed to generate those lookup tables. And every time somebody says something like that, I just think, oh my God, you know, if there's a factor 2 error in hydrolite, I have like totally blown NASA away. I'm going to be banished to some island in Antarctica or somewhere left to die. Okay, so anyway, there's a lot more of this on the web book or whatever, and we're going to talk more about this on Friday. So you'll also see other AOPs, one of which is this family called average or mean cosines. And what those are basically you've got a radiance distribution in the water. It's got some angular distribution. That's a whole big function of theta and phi. And you'd like to have just some one number that says, well, this radiance is kind of going downward or it's going off to the side, whatever. And so people they take a radiance distribution and they say, I want to get the average cosine. Cosine meaning from the nadir direction measured outward. So for this radiance distribution, what's the average of that cosine? Now, if all the light's going straight downward, cosine's 0, or theta's 0, so cosine's 1. If the light was going out here at 60 degrees, cosine of 60 is 0.5, so that if all the light was going at 60-degree angle, then the average cosine would be 0.5. So anyway, they just thought, well, let's try this. Give me the radiance distribution. I'll plug in a cosine and I'll average it over, let's say, all the downwelling directions. So there's radiance to cosine, sine theta, d phi. That's our element of solid angle. And then we're going to normalize that by the radiance integrated over all directions. Notice this thing in the numerator, that's just the definition of ED. And this thing down here in the denominator, that's just the definition of downwelling scalar irradiance. So this mean cosine is really just ED over E0D. And you can do the same thing for upwelling radiances, or you can do the same thing for the entire radiance distribution, where now notice that over the downwelling directions from here out to here, theta is less than 90 degrees, the cosine's positive, but from 90 to 180, the cosine's negative. So you actually end up with the mean cosine of the whole radiance distribution being ED minus EU over scalar irradiance. And these mu bar D, mu bar U, and mu bar, you will see in the older literature a lot of times. I don't think anybody uses them for too much anymore, but you still will see them around. And notice that the scalar irradiance, the total, is equal to the downwelling plus the upwelling, but the mean cosine of the whole radiance distribution is not the mean cosine for downward plus the mean cosine for upward. Okay, so here's once again the idea. If the radiance is heading mostly straight downward, you have a small theta and a large mu bar D. If the radiance is more out to the side, or if it's more diffuse, you'll have a bigger average cosine and therefore a bigger theta and therefore a smaller average cosine. And if the radiance is isotropic, you can plug in the numbers, do those integrals, and mu bar D and U will be 0.5 and mu bar will be 0. Okay, enough said. So what do these look like? Well, our same simulations, some different sun angles, different chlorophylls. These guys have different values. So the solid is mu bar D, the dotted is mu bar U, and the dashed curves are mu bar. So, and these things, once again, as you go to depth, they become AOPs. Enough said on that. And so here's just some little simulations. You haven't seen it yet, but I said that KD is a very absorption-like parameter. And there's a thing called the quasi-single scattering approximation developed by Howard Gordon. And if you work through that, it'll show you that the first order, KD, looks like absorption plus backscatter over the cosine of the sun angle in the water. And that'll get you about 80 or 90% of the total answer. The reflectance, on the other hand, is proportional to BB over A. And that makes sense because I'm looking at a reflectance, so the stronger the backscattering light is, the more is going to come back upward, and that's going to be my EU. But the stronger the absorption is, the less light's going to get reflected upward. So you can just reason that higher backscattering and lower absorption will give you a higher reflectance. Okay, so I put in a profile of IOPs here where I have an absorbing layer at 5 meters, and then I have a non-absorbing but highly scattering layer at 15 meters. So now, so this might be like a lot of little quartz particles. It might be a lot of little bubbles, for example, but non-absorbing, highly scattering, and highly absorbing layer here of CDOB. So highly absorbing but non-scattering. So what's KD going to look like if I measured in the water and used the EDs to get a KD profile? So we're going to come in, the light's going to start decaying. It's going to go through this highly absorbing layer. So that's going to really decrease the light field, and that'll make a high KD. And then we'll come out the bottom and it'll just be the same rate, whatever's down there. So here's KD. It comes in, and this is computed, not just from that formula, but out of hydrolite. So here's KD, and it tracks very nicely with the absorption. So going through this, light's being absorbed very strongly means a high KD. We come out here, well, there's a little bit of a bump in KD due to the backscattering here, but it's pretty small compared to the absorption. So as I said, KD is a very absorption-like AOP. What does the irradiance reflectance look like? Well, here it is. Notice it's got a peak, but it's above the scattering layer. So what you're seeing here is we're getting a lot of backscattering in this layer, which is making a high EU just above the backscattering layer. And then up here, of course, absorption is high, so it really knocks the reflectance down to basically 0. And then you come out down here, you start seeing the ED that's coming from the backscattering by this layer, and then you get below it, and it's kind of constant from there on down. So if you just, play around with these kinds of profiles, you kind of start building up intuition about what an AOP like KD or R might be telling you about the profile of the IOPs in the water. Now here's another, yeah.
Back a second. The relationship R equals BB over A was for the reflectance at the surface provided.
Well, this is the BB over A is whatever depth you're at.
But that's whatever the right is.
Yeah. So that's just the,
I thought it was around the right, you did the right for the surface.
well, yeah, when you start sticking the 23s and stuff on there, they were really interested in at the surface. But the 23 is more what you would need to get it at the surface. But if you go down to 50 meters, it still depends on BB over A. Might be 0.5 or something different.
Yeah, so it doesn't look really fits as well as the other relation.
But after you can learn to run hydrolite, just do simulations like this and look at BB over A and the computed R as a function of depth and see, instead of the same proportion, what's the actual proportionality constant, and see what it looks like. Yeah.
At least in this example, like, could you ever even measure R below? Like, all the light would be gone, right? So, like, unless you had an active light source or something.
Well, no, this is sunlight coming in at the surface and then decaying with depth.
All right, but, okay. It just, like, that absorption is almost 1 over 1 meter, right? Like, wouldn't there be no light in the water column?
Yeah, I guess, I mean, in the simulation, we've got sunlight coming in at the surface, and ED and EU and so forth are decaying with depth. And, but there's still light down at 25 meters, just however much got down there. Yeah.
Just from a little bit to retain cosines, do you have to include that in your version?
Yeah. Not your question.
In your version of AD, do you have to include the cosines?
No, No, so all, to get the KD, you either have your measurements of ED and you compute a depth derivative, or it's being done by definitions inside Isotropic. But you don't have to, like if you give me an ED profile of depth, I just take and get the depth derivative there. I don't have to stick in cosine factors or anything like that.
Even with minimum angular distribution.
No, because this, the ED is, that goes into the KD, it's just whatever was measured. And so, you know, if I wanted to compute the ED given the radiance distribution, that's where I stick in the cosine to do the integration. Okay, so here I plotted KDs and KUs, and here's 0. So notice the KD is positive because ED is always decaying with depth. But now what does it mean that the KU started out positive, but then it went below 0 and then it went above 0 again? So what does a negative KU mean for EU? Positive K function means the light field's decaying with depth. A negative K function means the light field is increasing with depth. Well, can you have light increase with depth? The answer is yes. You don't see it in the middle of the ocean on a normal day, but it's easy to see in two cases. Here, we had this highly scattering layer at 15 meters. So I start out near the surface. I'm gonna point my instrument downward and measure EU. So it starts out, I go down in the water, it's getting darker and darker and darker. So KU is, whoops, KU is positive. But then I start seeing the effects of this highly scattering layer sending a bunch of light back upward. So EU actually starts getting bigger as I get towards the scattering layer. And that's where the KU goes negative. Now, the other place you'll see this is if you're in, let's say, 10 meters of water and there's a sandy bottom, and you're measuring LU, for example. You start out near the surface, instrument goes downward, LU is getting smaller and smaller, and then you get down close to the bottom, the LU will start increasing. And that's because of the irradiance reflected off of the bottom. So it actually looks brighter as you get close to the bottom. So you don't see that in infinitely deep water in normal ocean conditions, but you'll often see it if you have a bright bottom, that your K functions will be negative. So here's the actual irradiances. Here's ED, it goes through the absorbing layer, it decreases, and then it's about the same below that. But here's EU, starts out decreasing, and then it starts seeing that scattering layer at 15 meters. So it actually is increasing here, and then it finally gets through that and starts decreasing again. Okay, here's, I think we're just about done here. I'm just gonna skip through these very quickly. It's another case where I did a simulation, I put in some values, and here's the 0, the black line. KD was positive, R was positive, but KU and KLU started out positive and they went negative. And here's the mu bar D, it's up around 0.7 or 0.8. But mu bar U, somewhere around 0.5. And you'll notice here, the R went to 0.15 and the mu bar U went to 0.5. And you don't know yet what a Lambertian reflector is, but a Lambertian reflector means that whatever light comes in, it gets reflected off equally in all directions. So that's making an isotropic radiance distribution, and an isotropic radiance distribution has a mu bar D of 0.5 if you plug in the numbers. Okay, so what's happened is I put a reflecting bottom at 15 meters. It had an irradiance reflectance of 15%, and it was a Lambertian reflector. So I got these profiles, and the reason the upwelling Ks went negative is they're starting to see the bright bottom. Okay, enough said there. Here's the ED profile. Here's EU starting to see the bright bottom and starting to increase. LU starting to increase a little bit. So you can get almost anything you want out of a light field if you just play around with the boundary conditions and what kind of IOPs are in the water. And you can always cook up some weird extreme case of highly scattering, non-absorbing, or highly absorbing, non-scattering, or whatever, and you can get just about anything you want for a light field. Okay, so I already gave you the answer there. That last one, the light was coming in, going off in the same in all directions, and that's what you got. The one thing to remember is IOPs, the total is equal to the IOP of the water plus IOPs, absorption for phytoplankton plus absorption for CDOM, whatever it is. AOPs, the total remote sensing reflectance, for example, is not equal to the remote sensing reflectance of pure water plus the remote sensing reflectance for phytoplankton plus the remote sensing reflectance for CDOM. It just can't be broken down like that. So just remember, IOPs are additive. You can measure them in a bucket of water. AOPs are not additive, and you have to measure them in the ocean. Okay, so I decided, since most of my late 20s, 30s, and 40s were all spent climbing. So every weekend and every vacation was go climbing. And I met my wife climbing. She saw me up on the rocks, and she thought I had nice legs, and it went from there. So, and then I found out she was a law student, and I had visions of marrying a high-powered attorney who was going to make like $250,000 a year. So it was just like a done deal immediately. It didn't turn out that way, but anyway, 45 years later, we're still at it. So anyway, I thought, well, when I moved the old folks home, I can't tell people that I was a mountain climber because they'll all say, well, did you ever go to Nepal? So I have to say yes. So I went over did a trek in Nepal in what's called the Annapurna Sanctuary, which is a sort of big, it's an enormous valley. It must be about 50 miles, 30 miles to 50 miles long. And it's a sort of very well-preserved area. And the local ethnic group there is called the Gurungs. And so they kind of run this show themselves, and they make money off of tourists like me. So anyway, I went up to there. We took us 11 days from the road up to where this was photographed at a place called Annapurna South Base Camp. And I have to, hang on here. I've lost my cursor. Where did it go?
Yeah, we can see it for you first.
Well, just a second. PowerPoint's decided it won't run this inside PowerPoint anymore. But anyway, I went up to this Annapurna base camp. We're at about 14,000 feet here. Yeah. Okay, anyway, so I'm at about 14,000 feet here, and I got up at some outrageous hour of the morning to watch the sunrise on Annapurna, which is another 13,000 feet right there to get you up to 8,000 meters. And so, well, now it's on here. I'm seeing the sunrise here, but not on the screen. Whatever Xiaom did.
I think you just need to drag it.
Yeah, see, we're not seeing what's up there, what's on the screen. anyway, so, and now it's disappeared on the screen. So anyway, I got up to watch the sunrise on Annapurna, which was just utterly spectacular. It was just one of these crystal clear, very cold days of just the most beautiful scenery you've ever seen. So
You wanted to play again?
I highly recommend.
Do we just put it up on the main screen?
Yeah, we want to get rid of what's there. Kill that guy. Anyway, yeah, hang on. I'm done with this thing. I will never again update software on Microsoft. I swear to God.
What do you want? You want
Close
to
that window and get back to here now.
I think it's not playing anymore. It's like,
Yeah, I'm done. Yeah, see that thing.
let me just play it this way.
There we go. That should get us. Yeah, okay. So when you get up to this South Annapurna base camp, I believe there's 7,000 meter peaks. They're just like bang, 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 bang. And then in the middle of it is the main Annapurna peak at 8,100 meters. It's the most spectacular place you've ever seen. This is Machu Picchu, the fish's tail, which is another almost 7,000 meter peak. And, you know, I just watched the sunset on this thing one night, and it was just spectacular beyond all description. So a very good trek. And at the end of the trek, hang on here. Let's see, slideshow. Well,
You just want the next slide?
that's what I'm doing. So I'm seeing it here and it's not coming through there.
Press the arrow on the.
Okay, so anyway, after playing around in the mountains, we sort of spent a week in Kathmandu, a couple of weeks on the trek, and went down and rode around on elephants and looked for rhinos. So that's a rhino. It's like from here, from me to you. And those things are huge. There's a rhinoceros track, and there's my hat. And it's like, the tracks are like this big around. And I kind of found that like elephants don't like stir up anything emotional. They're kind of like big cows. But rhinos, this thing is like a dinosaur. And you see this rhino and it's just like, you know, the hair stands up on the back of your neck. It's such a monstrous thing. They're like this high, and they have terrible eyesight. And when their ears point towards you, they're like sensing you. And that's like the rhino's way of saying, you're in my space, it's time to back off, is when the ears go around. So anyway, I didn't get in any bad shape with this guy, but we had a couple of elephants, and the people on the other one of the rhinos had a little baby, and the baby kind of ran around the back of the elephant. And so the elephant was in between the rhino mother and the baby. And then the rhino mother freaks out, charged the elephant because, you know, it's protecting the baby. So the rhino charges the elephant. The elephant rears up on its back two legs with this rhino right down there, and the little baby's running off in the woods. She's freaked out. And it was about an interesting 3 seconds where until the, you know, rhino backed off and the elephant went back down, and baby and mama were reunited. So anyway, that's quite the place. There's a saying, the first time you go to Nepal for the mountains, and the second time you go back for the people, because the people are just absolutely fabulous. And I attribute that to being in kind of the part I was in is a dominant Buddhist culture. And it's just a different view of how the world works than what we get over here. So that's my story for today. And it's now 10:30. So Ken's up quarter till then.